students. Today, ladies and gentlemen, we are going to be talking about machines. This week, we are going to be exploring various aspects of different kinds of machines. So we're going to begin today. So open up your books to your notes page and let's get started with machines, shall we? So machines, when you think of a machine, I'd like to ask you a question. What do you think of when you think of a machine? You probably have many different thoughts going through your head, and I'm sure you listed a number of different kinds of machines that you are exposed to and you utilize and take advantage of every day of your lives. Machines are all around us. We can't escape them. We as human beings love to use machines. And there's a reason for this, which I'll get to in a moment, but I just want to point out this video, if you have not watched it yet, you've got to watch it because it is an awesome music video dealing with what's called a Rube Goldberg device, which is a series of machines all working together. And it's a very complex apparatus, but it's certainly worth the watch if you haven't watched it already. So check out the notes and click on that hyperlink. It's pretty awesome. But so why do we use machines? Well, unlike this video, machines are intended to make work easier for you, more straightforward and simpler, but certainly easier from the standpoint of science and physics. And we're going to be talking about exactly what that means. But how about I give you an example here of how a machine can be an instrument that makes work easier. So let me go over to the close-up view in our lab right now. And you'll notice in front of me, I have a block of wood. And behind this block of wood, I have a nail, just an ordinary nail. Now, I could try very hard to take this nail and to push it or apply a force to this nail to try and get it to stick into the wood. I'm going to try one more time here. I'm going to push as hard as I can with my finger on this nail, but the nail doesn't stay, and all I get is a thumbprint on my thumb because I just can't apply a great enough force to get this nail into the wood. So what do I need to do? Give me an answer. How can I get this nail into the piece of wood? Yeah, you probably mentioned, well, use a hammer, because a hammer is an instrument that will make the work of getting this nail into the piece of wood a lot easier. So let me give it a try. Well, what do you know? It worked. The hammer is an example of a machine because it made the work applying a force through a distance. It made that easier for me to accomplish. So a hammer would be a great example of a machine that makes work easier. So let's head back over to our notes now. All right, so a machine, what is it from a scientific point of view? A machine is an instrument or a tool that makes work easier. Again, remember, what is work? Applying a force over a distance or through a distance, force through a distance. So here's an example of another instrument or a tool, a power drill, and certainly a power drill is going to be a lot easier to screw in a screw into a piece of wood as opposed to trying to do it with your bare hands. That would be a rather difficult challenge for anyone to accomplish. So let's illustrate this visually. We've got a machine that is in the middle of putting work into something and getting work out of something. In the example I gave you before with the nail and the piece of wood, the work that I was trying to put into the system was simply moving a nail, applying a force to a nail, and moving it through a distance. That was the work input. Initially, I tried to use my finger, didn't work too well. So what did I use? I used a machine. Machine can be as simple as a hammer in order to get a certain amount of work out of a system. So that's the basic premise, the basic idea, the basic definition of a machine to make work easier. But there are limits. There are limits to this. Let's go back over to the close-up view for a moment, and let me give you another example. I have another machine here, which happens to be a toy. And I want you to watch this toy. It's kind of a top. Hopefully you can see that. I love toys. Now, I am applying a force through a distance to make this top spin around. Now I'm going to stop applying a force, and what do you think is eventually going to happen to this spinning top? If you said it's eventually going to stop, you are exactly right. My question to you is, why? Think about that for a moment. Why did this eventually stop? All right, perhaps some of you came up with the answer of friction. Friction eventually makes this little toy stop moving. And guess what? Friction is the enemy of all machines. Because here's the deal. You get a certain amount of energy being put into a system like a machine. It does something, it does a process for you, and you get a certain amount of energy out of it in the form of whatever task you're trying to do. But there's always some loss. With any machine you use, there's always some loss. So we've got to understand this concept of efficiency to get a better idea of how we can use machines to our advantage. So let's talk about efficiency here for a moment. Efficiency is a comparison. Now, in math class, when you think of comparisons, you might think of fractions mathematically. That would be a good thing. It is a ratio. Efficiency is a comparison of work output to work input. And by the way, this is another great video for you to watch in case you didn't watch it on Monday. So this comparison of work output to work input. Remember what I said a comparison is? A ratio. Think of mathematics. How are ratios written? Well, here's the equation or the formula for efficiency. Efficiency is equal to the work output divided by work input. And whenever you see one thing divided by another thing, it's essentially a fraction. We've got a fraction or a ratio or a comparison of work output to work input. Now, I grew up on the Star Wars movies when I was younger, when I was your age, and I always remember the little characters called the Ewoks. And I think that was was it in the first movie or the second movie? I don't even remember anymore. But the little Ewoks, the fuzzy little cute critters. And I think of Ewoks when I think of efficiency in this equation because they made a silly little noise, and I'm going to try to replicate that silly little noise now because it's the way I remember the equation for efficiency. It's Ewo wee, Ewo wee, E whoa wee, E whoa wee, E whoa wee. Everybody say it with me. E whoa wee, E whoa wee, E whoa wee. I know if you don't want to sound like a little Ewok, you'll want a deeper voice, so you can say E whoa wee. Everybody say E whoa wee. Okay. E whoa wee is the correct formula for efficiency, where efficiency is again compared to work output and work input. The W sub O stands for the work output. W sub I stands for the work input. And E stands for efficiency. But as I just alluded in that little slide preview there, E or efficiency is never equal to or greater than 100. Efficiency can never reach 100%. Some efficiency is always lost to friction. So the reason our little toy here could not continue to spin around forever and ever. Now I can't even get it started once. Here we go. All right. The reason our toy can't spin around forever and ever and eventually stops is because of friction. All machines, friction is its enemy. Friction, that force moving in the opposite direction as a moving object, that force of friction is what causes all objects to eventually stop. Let me give you another example here as we do another close-up view, and I bring out another one of my little toys. Imagine having a car or a motorcycle or bicycle or what have you, and this little toy, this little Harley Davidson toy here, works in a really cool way. See the helmet on the back of it? When I pull the helmet, it turns a flywheel, which boink, turns the back wheel, and woo, and let's do it again. And whoa, the motorcycle rides on the road. It's a great toy. Really cool to jump ramps on this too. But here's the deal. I can pull this, apply a force, and cause it to turn really fast. Eventually, however, it's going to stop. And why is it going to stop? It's because of friction. And that friction has a byproduct to it with machines. And that byproduct is always going to be the stopping of the object, and there's always going to be a release of heat energy. In fact, I can touch this back wheel right now, and I can feel that it has gotten a little bit warm. Why? It is because of friction. I can come back over to the computer now, and if I touch the computer, I can touch the computer, take my word for it, I'm touching the computer, and the computer is a little bit warm right now as well. And why is that? Well, it's plugged in, it's using electricity, and a computer is not 100% efficient. And so as a result, there is some friction from the electrons flowing through the wires. And that friction is causing the release of heat energy. So even electrical machines like my computer are losing efficiency because of friction. By the way, there are lots of scientists out there trying to develop supercomputers which are as close to 100% efficient as possible. And they're trying to operate these to utilize the least amount of energy possible. There's a lot of money in that. It is estimated that the cloud, meaning that virtual storage place, which is made up of lots of supercomputers, releases a significant contribution to the greenhouse gases in the atmosphere because of the electrical friction resulting from all of the electricity that's used to operate these supercomputers. So think about that the next time you're using your smartphone and you're saving pictures to the cloud. You are contributing to the greenhouse gases in the atmosphere. That's a topic for another day, obviously. But the point that I'm trying to make is that all machines, whether they are mechanical, simple machines like a hammer, whether they are automotive machines like a motorcycle or car, or the machine that you're using right now to view me, whether it's a projector or a Google Chromebook or a computer, phone, whatever, that machine also is not 100% efficient, and there is a loss of efficiency due to friction. Whether it's physical, mechanical friction, electrical friction, doesn't matter what, every machine loses efficiency. All right, I think we've beat that like a dead horse here. Efficiency. You will be calculating efficiency, however, and I do want to make sure I point something out here with efficiency. I made the comment that efficiency never reaches 100%. Efficiency has no units. You're taking work and dividing it by work. And so as a result, the units cancel out and you just get a numerical value for efficiency, and we express it in terms of a percentage. So efficiency is always expressed as a percentage with no units attached. All right, you'll have to forgive my my verbosity there, my lengthy words, and my scattered thoughts there for a moment. But someone was trying to get my attention on the phone, and I was trying desperately to ignore it. But I was a bit distracted. But you've got my full attention once again. So let's move on to our next little topic, which is mechanical advantage. And to introduce mechanical advantage, I want to go back to our virtual lab and show you a little example here. Okay, so we're going to go back to our close-up view, and I want to show you something. I have two objects here. They are brass masses. I think you can see them well enough. These brass masses both have a mass of 1 kilogram. And I'm going to bring in an object here, which is going to be a fulcrum to a lever. We could also call this lever a seesaw or a teeter-totter. And on one side of this, basically a piece of wood that I have balanced at the midway point, I'm going to put a 1 kilogram mass on one side of this piece of wood. And what do you think I'm going to need to put on the other side of the piece of wood to balance out the 1 kilogram mass on the side that is now down? What do you think I'm going to have to put on the other side to balance it out? Yeah, the other kilogram mass. In fact, I'm going to do that right now. I'm going to position them both on in the center here. And I think you can see that the 1 kilogram is balanced with the 1 kilogram. There's 1 kilogram On this side, there's 1 kilogram on this side, and they are both equal to one another, right? I mean, that's pretty easy to see. If you want to ride on a seesaw and you don't want to get stuck up top, you want to find somebody that has about the same mass as you to be on the other end. Now, what if I were to take this 1 kilogram off and bring over a 500 gram or a half a kilogram over? Do you think that I can balance this lever again if I were to put this 500 gram or 0.5 kilograms over here? In other words, I'm going to ask you a question. What do you think is going to happen when I let go of this lever? If you answered that the kilogram is going to go down, you're absolutely right. Absolutely, yeah. That 1 kilogram certainly has a bigger mass than the half a kilogram. But did you know that there is something that I can do to this lever in order to balance out this kilogram with only a half of a kilogram? Do you notice what I've done here with our lever? I've put 1 kilogram on one side and a half a kilogram on the other side. What have I done differently with this machine? If you noticed that I moved this block, this fulcrum, closer to the larger mass, you're exactly right. I have turned this little seesaw into a machine simply by moving this fulcrum over. And I am accomplishing a task of lifting 1 kilogram with only a half a kilogram. I think that's pretty cool. That's using our noggin, if you think about it. Now, what if I were to put that 500 kilogram off to the side and bring over a 50 gram mass? Do you think I'm going to be able to balance out a 1 kilogram with a 0.05 kilogram mass? What do you think is going to happen if I let go of it? Yeah, the kilogram. Whoa! Did you see that? The big kilogram threw the 0.05 kilogram mass off pretty significantly. But notice what I'm doing. If I move the fulcrum over enough, check it out. 0.05 kilogram mass is enough to balance out an entire kilogram. I think that is pretty awesome. Now, it was Archimedes who said many years ago, "Give me a lever long enough and a place to stand, and I can move the earth." And you know what? Mathematically speaking, theoretically speaking, scientifically speaking, he's entirely right. If he had a place to stand, a firm place to stand, and a lever that was long enough, he could literally move the entire planet Earth. Now, from a practical point of view, it's really not possible, but his point is well taken. You can use a lever like a big stick, maybe, and if you had a big old rock in your yard that you had to move, and there is no way you could lift it by yourself, you could use that big stick, and if it were long enough, you could apply a great enough force to one side in order to lift that rock and put it wherever you want. That's the idea of mechanical advantage. Using machines to your advantage. So let's head back to our notes and talk about this a little bit more. So what is Mechanical advantage, oops, wrong button. Mechanical advantage is how much a machine multiplies the effort force. Now remember, what is a force? A push or a pull on an object. So pushing or pulling on an object trying to accomplish something is called your effort force. And you can make yourself a lot stronger, in a matter of speaking, by using machines. And there's lots of superhero movies out there where you've got machines being used to multiply the effort force of their user in order to accomplish some superhuman strength, like flying or tearing apart buildings or whatever the case might be. But there is an equation for mechanical advantage, and here it is. Mechanical advantage, abbreviated by capital M, capital A, is equal to the resistant force divided by the effort force. So F sub R is the resistant force, F sub E is the effort force. Remember, the effort force is how much you are actively pushing or pulling on something, and the resistant force is how much the other thing is pulling or pushing against you. And it is the machine that enables you to increase or decrease, as the case may be, the mechanical advantage in order to make a job easier or more difficult. There are times when you would want a smaller mechanical advantage rather than a bigger mechanical advantage. And we'll discuss that later. So once you have this written down, there's a phrase I want you to remember, and it is this: the higher the mechanical advantage, the easier it is to do the work. The bigger or the higher the mechanical advantage, the easier it will be to do work. We're going to be doing a lab tomorrow, or in a couple days. In 2 days, we're going to be doing a lab activity, and we're going to be using machines. And we're going to see how a higher mechanical advantage is going to make the work easier. But remember, what is work? Remember, the work is a force acting through a distance, or force times distance. Okay? So, mechanical advantage is equal to what is it equal to? You tell me. What is mechanical advantage equal to? Resistant force divided by effort force. And the higher the mechanical advantage, the easier it is to do work. So here's a couple pictures to help illustrate mechanical advantage. The first example is of a lever, very similar to the one that I illustrated in the close-up of the lab. Here we have a lever, kind of like a seesaw. The 1 kilogram mass demonstrates the resistant force. The resistance force was the force being pulled down by gravity that we wanted to lift, or in our case earlier, to balance out. And we had to balance it out using an effort force. And that effort force was different based on the location of this device called the fulcrum, which we'll get into more tomorrow. But moving that fulcrum, we were able to essentially increase or decrease our mechanical advantage. Likewise, with a pulley system, we have a resistant force, F sub R, some object that you might want to lift, and we lift it by applying an effort force. So our effort force is what we are pulling down, and the resistant force is the object being pulled down by gravity. So we've gotten through quite a bit here today. with mechanical advantage, efficiency, and the general definition of machine. So we're going to stop here for today. And tomorrow, we're going to pick it up by going through a list of simple machines. So for today, I'm simply going to say bye.